So today, we will give a conjecture on explicit forms of polyhedral realizations for crystal bases of quantum groups in terms of monomial realizations. So these crystal bases, denoted by P of infinity or lambda, they are powerful two-study representations of quantum groups. And this polyhedral realization is one combinatorial description of P of infinity, and the monomial realization is a description for P of lambda. So there are several keywords like polyhedral realizations, crystal base, quantum groups, and monomial realizations. So we will explain them one by one. So first, we consider quantum groups. And next, we review crystal base and polyhedral realizations. And next, we recall monomial realizations. And finally, we'll give main results. And it includes the conjecture stated here. And we also explain this conjecture is true in several cases, like classical Lie algebra or classical affine Lie algebra. So let us review quantum groups. So we start with Lie algebra. So Lie algebra, denoted by G, is a vector space over C with bracket product. This product must satisfy these two actions. The first one is the product of x and x equals 0. And the next one is called Jacobi identity. The first, we review finite dimensional simple Lie algebras. And generalizing these algebras, we can get Kac-Moody algebras. And by quantization of finite dimensional simple Lie algebras, we also get quantum groups. And considering Kac-Moody setting and quantization, we can also get quantum groups for Kac-Moody algebra. So let us review first one. So this simple means G has no ideal other than 0 and G. So for example, G equals SL2 of C is an example of finite dimensional simple Lie algebra. So it is a vector space of 2 times 2 matrices whose trace equals 0. And defining bracket product xy as xy minus yx, then if x and y are in G, then the product of them also belongs to G. And putting E, F, H like these matrices, these are bases. In particular, these are generators of G. So by direct calculation, we can easily check these generators satisfy these relations. And actually, for arbitrary finite dimensional simple Lie algebra has a similar structure to SL2. That is, if G is a finite dimensional simple Lie algebra, then it has 3 n generators, EI, FI, and AGI. And here I belongs to index set I equals 1 to data n. And these generators satisfy these 6 relations. And note that Lie algebra G has G satisfies only these 6 relations essentially. So essentially means other relations can be obtained by combining these 6 relations. And here, this AD means adjoint action, and this AIJ is an element of the matrix A, and it is called Cartan matrix. And this matrix satisfies these 3 conditions. The diagonal elements are 2, and other elements are non-positive. And if AIJ equals 0, then AJI also 0. And AIJ is symmetrizable. That is, there is some diagonal matrix D such that dA is symmetric. And this symmetric matrix dA is positive definite. So in this way, using Cartan matrix, we can uniformly state the structure of finite dimensional simple Lie algebra. So it is interesting problem how many matrices satisfy these 3 conditions. The matrices satisfying these 3 conditions are classified by thinking diagrams like this. So this is a list of thinking diagrams, and each diagram represents some matrix. The rule of correspondence of matrices is as follows. If in these diagrams, if the vertices I and j are connected by single edges, then it means aij equals aji equals -1. If they are connected by arrow from I to j with double edges, then aij equals -1, aji equals -2. And if it is triple edges, then it means aij equals -1, aji equals -3. And if I and j are not connected, then aij equals aji equals 0. So each diagram represents some matrix. So combining this result and this result, we can say that finite dimensional Shiburi algebras are classified by thinking diagrams. So in this way, the structure and classification of complex finite dimensional Shiburi algebras are well known. And we can say that the theory of finite dimensional Shiburi algebras are quite successful and beautiful. So we can expect the following. So considering the natural variations of finite dimensional Shiburi algebras, we can expect that we can obtain some new interesting theories. So there are several variations, and today we consider these three variations. So first one is Kac-Moody algebra, so which can be obtained by removing the positive definite condition for Cartan matrix. So recall that if there is finite dimensional Shiburi algebra, then it is classified by matrices satisfying these three conditions. And this removing positive definite condition means we drop the condition for symmetric matrix DA. So this is positive definite. So removing this condition, we can get Kac-Moody algebra. So we can also drop the condition of symmetrizable, but today we'd like to consider quantum group. So we don't drop the condition of symmetrizable. And there are another direction of variation. So it is quantization. So applying quantization for finite dimensional Shiburi algebra, we get algebra called quantum group. And we can consider, I'm sorry. We can consider that these two variations simultaneously. Then we get quantum group for Kac-Moody algebra. So first, let us see Kac-Moody algebra. So as I said in the previous slide, we take matrices, matrix A equals Aij like this. The first condition and the second condition are same as in the finite dimensional case. And the third condition is just symmetrizable. That is, the condition for DA's positive definite is dropped. And to consider this algebra, we use the following. So let's have here 2i minus rank of a dimensional vector space over C, and we assume that hi and dj are base of her. And let alpha I in her star, so this is dual space of her, such that alpha j of hi equals aij, and alpha j of dk is 0 or 1. Then we can define a new algebra. So let K be a real algebra with generators ei, fi, and her, such that for h prime in her, these six relations hold. Then K is called a symmetrizable Kac-Moody algebra. So in the theory of abstract algebra, there is a procedure to define the algebra from the formal symbol like ei, fi, or her with relations among them. So following such relation, we can formally define the algebra, and in this case, we called it symmetrizable Kac-Moody algebra. And note that if this H and H prime are Hi and Hj, then these six relations coincide with the previous relations in the finite dimensional simple Lie algebra. So we can consider Katsumudi algebra as the generalization of the finite dimensional simple Lie algebra. And unlike finite dimensional simple Lie algebra, in general, Katsumudi algebras are infinite dimensional. And all non-trivial representations become infinite dimensional. And in particular, there is a special classes in Katsumudi algebra called affine Lie algebra. If we take A as the symmetric matrix, dA is non-negative definite and not positive definite, then G is called affine Lie algebra. That is, we take a matrix A which satisfies first and second condition, and Aij is symmetrizable, and symmetric matrix dA is non-negative definite one. Then we get affine Lie algebra. So it is also interesting problem how many matrices satisfy the condition for affine Lie algebra. So such matrices are classified by affine thinking diagram. So I didn't write the all diagrams, but there are 14 kinds of diagrams which are named by alphabet from A to G with upper index and lower index. Okay, so this is the story of Katsumudi algebra. And there is another variation. It is quantum groups introduced by Twinfeld and Jimbo independently. So roughly speaking, it is a similar algebra to K with indeterminate Q. So let RQ and RQ factorial and MRQ be this rational function of Q. So if we specialize Q to 1, then R of Q coincides with integer R, and this coincides with R factorial, and this goes to binomial MR. And let K be a finite dimensional simple Lie algebra, and let Yuki of K be C of Q algebra with unit 1, with generators EI, FI, and Q of H, and H belongs to ZHI, satisfying these 6 relations. So as I said in the definition of Katsumudi algebra, there is a procedure to define new algebra from formal symbol with relations between them. So following such a procedure, we can define a new algebra, and it is denoted by Yuki of K and called quantum group. And today I didn't explain the detail, but if we specialize the indeterminate Q to 1, then we get relations of universal enveloping algebra of K from these 6 relations. So we can consider quantum group as Q analog of universal enveloping algebra. And quantum groups for Katsumudi algebras can be also defined by the same way as in the finite dimensional case. That is, we take A equal Aij and a vector space her and alpha I, just as in the definition of Katsumudi algebra. So that is, the matrix A satisfies these 3 conditions. And her is the 2i minus rank of A dimensional vector space with space Hi and Dj, and alpha I satisfy these conditions. And this is called simple root. And we can define quantum group by the same way as in the case against finite dimensional simple Lie algebra. That is, let Yuki of K be C of Q algebra with unit 1, with generators EI, Fy, and Q of H. The difference is here, so H belongs to ZHI or direct sum of ZBJ with these 6 relations. And these 6 relations are same as in the definition of finite dimensional case. So just as changing the matrix to non-positive definite one, then we can similarly define the quantum group for Katsumudi algebras. Okay. And today, I'd like to consider the representation theory of quantum group for continuity algebra. So recall that Yuki of K has a generator EI, Fi, and Q of H. And let P be weight lattice. That is, it is a set of element lambda in Hasta such that lambda of Hi and Dk are integer, and P plus is a set of dominant integral weight. That is, it is a subset of P such that these values are non-negative. And for each lambda in P plus, there exists a representation V of lambda such that there is an element V lambda, and it satisfies EI V lambda equals 0 for all I, and it is a simultaneous eigenvector for Q of H. And V of lambda is generated by the element in the form Fj1 Fjr V lambda. And this representation is an analog of finite measure British representation L of lambda for finite measure simple algebra. That is, L of lambda has an element L lambda, and it is vanished by the action of EI, and it is a simultaneous eigenvector for action of H, and it is generated by the element in the form Fj1 Fjr L lambda. So there is a representation V of lambda, which is an analog of finite irreducible representation. And today, we mainly consider such representation. And such a representation, V of lambda, has a crystal base V of lambda. And I will not explain the precise definition of crystal base. We just give a property of it. So first, V of lambda is a set with maps EI tilde and FI tilde, and they are called Kashiwara operators. So it is a map from V of lambda to V of lambda cat 0. So this 0 is kind of extra element which does not belong to V of lambda. And these are considered as combinatorial analogs of action of EI, FI on V of lambda. And there exists some element V lambda bar in P lambda, such that V of lambda coincides with a set of element in the form Fj1 tilde, Fjk tilde, V lambda bar. And it holds the number of elements in V of lambda coincide with the dimension of original representation V of lambda. And there is another map weight on V of lambda to B, such that the value of Hi on the weight of Fj1 tilde, Fjk tilde, V lambda bar, so it is an element of V of lambda. This coincides with the eigenvalue of Fj1 Fjk V lambda in V of lambda for Q of Hi. So from the information of V of lambda, we can get the dimension of original representation or eigenvalue of original representation. Okay, so this is a crystal base V of lambda for V of lambda. And today, we'd like to consider the one more crystal base, V of infinity. So it is for UQ minus, okay. So this is a subalgebra of quantum group generated by Fi. And as a property, Q of H is acting on UQ minus by conjugation. And since this algebra is generated by F, so each Fi is naturally acting on UQ minus by the multiplication from the left. And this algebra is not closed under the multiplication of EI. So we need to modify this multiplication, and we can define new operator EI prime on UQ minus, okay? And this UQ minus has crystal base P of infinity, and just as in P of lambda, we just give a property of it. And it is a set with maps EI tilde, FI tilde. So they are also called Kashiwara operators from P of infinity to P of infinity cap 0. And these are combinatorial analogs of EI prime and FI stated here. And just as in P of lambda, it has element P infinity bar such that each element in P of infinity is written as fj1 tilde dot fjk tilde V infinity bar. And there's another map weight on P of infinity and the value of hi on the weight of fj1 tilde dot fjk tilde V infinity bar coincide with the eigenvalue of fj1 dot fjk V infinity in uq minus k for the conjugation of qhi. And there's a relation between these crystals. So for any lambda in P plus, there is a map from P of infinity onto P of lambda, which is an analog of surjection from UQ minus to V of lambda. And it is defined by fj1 dot fjr is mapped to fj1 dot fjr V lambda. So as I said in the previous slide, by studying crystal base P of lambda, we know eigenvalues of P of lambda or dimension of P of lambda. And we can also get a structure of tensor product and so on from crystal base. And P of infinity also tells us the structure of the UQ minus. So in this way, studying crystal base P of lambda or P of infinity, we can get several important information of representation or UQ minus. So we'd like to study the crystal base. So to study crystal base P of infinity lambda, the combinatorial descriptions of them are useful. And these crystal base will have a bunch of combinatorial descriptions. And today, in particular, we'd like to consider polyhedral realizations. That is a description for P of infinity. And monomial realizations, it is for P of lambda. Okay. So first, we'd like to review polyhedral realization. So to define it, we need to fix the infinite sequence iota equals I1, I2 data. And each I1, I2 data is in the index set I. And let Z infinity be the set of number sequence A1, A2 data such that each element is an integer and it converges to 0. And we can define maps denoted by fi tilde, ei tilde. So they are the same notation as in the Kashiwara operator of B of infinity or B of lambda, but we can define maps fi tilde, ei tilde on Z infinity iota and weight on Z infinity iota. So in this slide and this slide, we define these maps. So here, weight is defined. And ei tilde, fi tilde are defined here. But so here, I will not explain the detail of these maps. The essential point is as follows. So above maps, ei tilde, fi tilde, and weight are defined by only sum of integers. In particular, we didn't use a representation theory. So even if we don't know the representation theory, everybody can compute these maps following above rule. So these rules are a bit complicated, but it is computational one. Actually, computable one. So we can define some computable maps on Z infinity iota. And there is a theorem. There is an injecting map from B of infinity to Z infinity iota, denoted by X iota, such that the highest weight vector V infinity bar is mapped to 0, 0, 0, da, da, da. And it commutes with ei tilde, fi tilde, and preserves weight. Recall that on B of infinity, these maps, ei tilde, fi tilde, and weight are defined. And in the previous slides, here and here, we also defined these three maps on Z infinity iota. So this theorem claims this psi iota is compatible with these three maps. So since this is compatible by this theorem, we can reduce calculations of these three maps on B of infinity, so which are important. Two, three maps on Z infinity iota, which are computable. And since this is computable, the image of psi iota is isomorphic to B of infinity as crystals. And this image is called polyhedral realization for B of infinity. So polyhedral realization means we express each element in B of infinity in terms of infinite sequence Z infinity. So this is an example. So we consider the case SL3. So this is a type A2 finite dimensional simple algebra. And we consider the sequence 1, 2, 1, 2, da, da, da. The crystal graph of B of infinity is as follows. So this is the highest weight vector, and this one implies the Kashiwara operator F1 tilde. So applying F1 tilde, we get this guy. And applying F2 tilde, we get another one. So in this way, we get a crystal graph, and it is an infinite graph. And to describe this graph, we need knowledge of representation theory of quantum groups. And this is a crystal graph of polyhedral realizations. So by psi iota, by map psi iota, this to infinity bar is mapped to 0, 0, 0. And applying F1 tilde, we get this number sequence 1, 0, 0. And we can calculate this number sequence following the computable rules stated here. And similarly, applying F2 tilde, we get number sequence 0, 1, 0, da, 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 and it is also computable. So, although we need knowledge of representation theory to describe this graph. About this graph, we don't need the knowledge of representation theory. And this graph, polyhedral realization, coincides with the set of number sequence A1, A2, A3, da, 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 and which satisfy these inequalities and this zero condition. So that is each number sequence appearing in this graph satisfy these inequalities and zero condition. And conversely, if a number sequence satisfies these inequalities, then such number sequence is appearing in this graph. So this inequality characterize the polyhedral realizations as said. So, and it is interesting because considering polyhedral realization or crystal base feature representation theoretical object, then some polyhedral cone is appearing, which are geometrical object. So because this equality means we can consider the polyhedral realization as a set of integer points in some polyhedral cone. So it is a natural problem to find the explicit form of such polyhedral cone. That is, we'd like to know the inequalities defining polyhedral realizations, such as this red inequality and zero condition appearing in this slide. So about this problem, many researchers tackled this problem. So for example, these researchers found that if Gates finite dimensional simple algebra and iota is this specific sequence, 1 to data n, 1 to data n, da, 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 then some explicit form of inequalities of polyhedral realizations are given. And classical affine type and iota is the same one. An explicit form of inequalities of polyhedral realizations are also given. And in the context of string cone, Littelman found as follows. So in the case Gates finite dimensional simple algebra, then this polyhedral realization coincides with the set of integer points over string cone. And in the context of string cone, we found that if iota is nice decomposition, so which is uniquely determined for the type of gate, then an explicit form of string cone is given. So this result means in this case, the explicit form of polyhedral realizations are also given. And in our previous result, if K is a classical real algebra or a classical affine real algebra, and iota is adapted, and I will explain about adapted later, then the inequalities of polyhedral realizations are combinatorially described by using column tableaus or Young walls. So these objects are introduced for the combinatorial study of representation of quantum groups. And by our result with Greg and Professor Nakashima, if K is a classical Lie algebra and for arbitrary iota, then we give an algorithm to compute the inequalities of polyhedral realization. So in this way, for classical Lie algebra or classical affine Lie algebra, some explicit form of polyhedral realizations are given. And to generalize or to consider the more general setting in this talk, we consider the case gauge a symmetrizable continuity algebra and iota is adaptive, and give a conjecture that claim the inequalities of polyhedral realizations are expressed in terms of monomial realizations. So now we already explained the polyhedral realization and continuity algebra. We need to give a definition of adapted and monomial realizations. So this is a definition of adapted. So we only consider the sequence which satisfies this adapted condition. So let A be a symmetrizable generalized pattern matrix, okay, and iota is some sequence. And if the following condition holds, then iota is said to be adapted to A. That is, for two indices I and j such that aij is negative, the subsequence of iota consisting of all I and j is either ji, ji da 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 or ij, ij da da. That is, the two indices I and j are appearing alternatively. So, for example, if gauge type A upper 1, 3 and iota is this cyclic sequence 3, 1, 2, 3, 1, 2, then the subsequence consisting of 1 and 2 are 1, 2, 1, 2, da, 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 1, 2, 1, 2, and that of 2 and 3 is 3, 2, 3, 2, da, 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 3, 2, 3, 2, da, da. So they are alternatively appearing. And that of 1 and 3 is 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3. So it satisfies this condition. So iota is adapted to A. So adapted is a slight generalization of the cyclic sequence like this. So today we only consider such a sequence. And defining adapted sequence associating with such sequence, we can also define monomial realization. It is another description of crystal base. So we consider the set of Roland monomials Y like this. So it is a set of Roland monomials xsi, zeta si. So each power is an integer, and except for finitely many si, each power zeta si equals 0. So just as in the polyhedral realization, we can define a maps weight fy tilde ei tilde on y associated with an adapted sequence iota as follows. So, so depending on the sequence iota, we define the data of Pij as follows. So it is they are integers such that Pij equals 1 if the subsequence of iota consisting of I and j is ij, ij. That is, it starts with I. Then Pij equals 1. And if it starts with j, then it equals 0. So depending on iota, we can define the system of integers Pij like this. And for each Roland monomial x, we can define a value of weight of x and fy tilde x and ei tilde x, like these slides, this slide and this slide. And just as in the polyhedral realization, we don't explain the detail of this definition. But the idea is essentially same as polyhedral realization. That is, to define these maps, fi tilde and ei tilde and weight, we don't need the representation theory. It is defined by only by using the data of monomials. So these maps, weight and fi tilde and ei tilde, are computable maps. And there is a theorem. If we take x as ei tilde x equals 0 for all I, and putting lambda as weight of x, and it is in p plus, then there is a bijection from p of lambda to the set of Roland monomials fjm tilde fj1 tilde x. And this bijection is compatible with these three maps. So as I said before, these three maps are defined on B of lambda, and which are very important to study the representation B of lambda. And in the previous slide, we also defined these three maps on the set of monomials, so which are computable. So just as with the polyhedral realization, using this theorem, we can reduce the calculation of these three maps on B of lambda to the calculation of Roland monomial, so which are computable one. So in particular, if we take x as single variable xsk, then we denote it by msk iota. So we define msk iota as the set of Roland monomials. And this is isomorphic to b of lambda k. Here, this lambda k means the fundamental weight, and it is defined by lambda k of hj equals delta kj, and of ds equals 0. So let us see some example. So we consider the same setting as in the example of polyhedral realization. So gauge type A2 and iota is 1, 2, 1, 2, Then this set of Roland monomial ms1 iota is expressed as follows. So this is the highest weight vector, and applying f1 tilde, we get this Roland monomial. And applying f2 tilde, we get this Roland monomial. And ms2 iota is expressed as follows. So it also has three elements. So these are example monomial realizations. And they describe the crystal base P of lambda 1 and P of lambda 2. And now we formally tropicalize these Roland monomials. And considering inequalities, trop of M is non-negative for all M appearing in these graphs. Okay. So for example, if we tropicalize xs1, then we get as1 is non-negative. And if we apply tropicalization to this Roland monomial, since tropicalization changes the subtraction to, tropicalization changes the division to subtraction. So if xs2 over xs plus 1 goes to as2 minus as plus 1, and we consider the inequality, this is non-negative. And from this Roland monomial, we get minus as plus 1, 2 is non-negative. And similarly, from these Roland monomials, by tropicalization, we get these three inequalities. And we consider these inequalities for all s in the set of positive integers. And then by the inequality, as1 is non-negative, as1 is non-negative, and minus as plus 2, 1 is non-negative. So combining these two inequalities, we get am plus 1, 1 equals 0 for all m, which is greater than or equal to 2. And similarly, from two inequalities, AS2 is non-negative and minus AS plus 1, 2 is non-negative. So combining them, we also get AM2 equals 0 for all m greater than or equal to 2. And simplifying another inequalities appearing here and here, we get this system of inequalities. So that is, most of variables equals 0, and another three variables, A11 is non-negative, and A12 is greater than or equal to A21, and which is non-negative. And now, we take variables like this double index variable A11, A12, A21, A22. So originally, it is a single variables A1, A2, A3, da, da, da. So these single variables are rewritten by double index variables. So rewriting these double index variable to single index variable, we get the inequalities. A1 is non-negative and A2 is greater than or equal to A3 and it is non-negative. Yeah, so from A11 is non-negative, we get A1 is non-negative. And from this intermediate inequality, we get this inequality. And these zero conditions coincide with this condition, AK equals 0. And recall that this linear inequalities characterize the polyhedral realization image of psi iota. So this example means we can get inequalities characterizing polyhedral realizations from monomial realization. From monomial realization by tropicalization. So again, so this example means we can get inequalities characterizing polyhedral realization from monomial realization by tropicalization. So of course, this is just example for type A2, but we'd like to give a conjecture this phenomena holds for general continuity algebra. So let us formulate it. So let iota be a sequence, and for single index variables A1, A2, A3, da, 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 we rewrite the variables AK by double index variable ASJ. If IK equals 0 and J is appearing S times in I1, I2, da, 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 IK. So depending on the sequence iota, we rewrite single index variable to double index variable. Yeah, so for in this example, the single index variable A1, A2, A3, da, 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 are rewriting as A11, A12, A21, A22, da, 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 so double index variable. So in general, we can rewrite it by this rule. And conjecture claims that so if G is a symmetrizable continuity algebra and iota is an adapted sequence, and let MSK iota be the set of monomial realization for GL. So this means continuity algebra whose generalized character matrix is the transpose matrix of that of G. So this L means a Lagrange dual. Then, so polyhedral realization can be expressed like this. So it coincides with the set of number sequence A in Z infinity such that phi of A is non-negative for all phi in trope MSK iota. So this trope is a tropicalization mark. So this conjecture claims we can get the inequalities characterizing polyhedral realizations from monomial realization MSK iota by considering the tropicalization. So this is the claim of conjecture. So if it is true, inequalities characterized with the polyhedral realizations are expressed in terms of monomial realizations. And for now, we partially show the conjecture. That is, when get the finite dimensional simple real algebra of type A, B, C, D, then the conjecture is true. So now we can check it. And if it is Katsumudi algebra of rank 2, then the conjecture is also true. And if again, the classical affine real algebra of type A upper 1, B upper 1, C upper 1, D upper 1, A upper 2 even, A upper 2 odd, or D upper 2, then conjecture is true. So in these cases, the conjecture is true. So before, I gave an example for type A2. So in this slide, let us see the case of type C2. And iota is the same one. Then first, the monomial realization MS1 iota is given like this. So from highest order vector, applying Kashiwara operator F1 tilde or F2 tilde, we get these four monomials. So this graph is for MS2 iota. So tropicalizing them, we get this system of inequalities. So for example, from xs1, we get as1, and from xs2 over xs plus 1, 1, we get as2 minus as plus 1, 1, and so on. So similarly, from these five monomials, we get five inequalities. And simplifying these inequalities, we get the polyhedral realization for type B2 is as follows. So this system of linear inequality and zero condition can be obtained by simplifying these inequalities. And remark that some Lagrange dual is happen. So now we consider gauge type C2, but the obtained polyhedral realization is type B2, which is Lagrange dual of type C2. So in this way, type B2 case is true. Sorry, this conjecture is true for type B2 case. And we proved this theorem by using the combinatorial description polyhedral realization. So in our previous study, for the case type A, B, C, D, or these classical affine type, some combinatorial description of polyhedral realizations are given. So using such a combinatorial description, we prove this theorem. And if for another Katsumudi algebra again, if we can give a combinatorial description of polyhedral realization, so I expect we can prove the conjecture stated here. Okay, that's all. Thank you very much.
Thank you. Questions? Yes, good.
Yuki, so in your
Yeah.
you consider monomial realization, so they look like monomials for Kirill-Fish-Tikin models for fundamentals.
Mm-hmm.
And so if we consider affine cases, so then we can look for Kirill-Fish-Tikin of infinite power of fundamentals, and then just consider monomials in such a model. So formally it's not defined, but we can formally define, so it's the dominant monomial, so it would be infinite product, but because computation goes from the leftmost, so therefore computation for any algorithm which we know can be applied, so therefore we just get a bunch of monomials, and so probably they will get us the answer for the.
So you mean we consider some kind of algorithm to some monomials which is not a single variable?
Yeah, so we consider Kirill-Fish-Tikin model with infinite power. So that means the dominant monomial would be like ti plus h, to infinity. But
infinite power. Okay.
Power,
infinite product. Okay.
Yeah. Dominant monomial is infinite power, and then my algorithm for computing for all monomials in this Kirill-Fish-Tikin model. Then we will get a bunch monomial corresponding to fundamental, because we know that we need for all, and then we do this for all fundamentals, then bunch of monomials, and then they probably give us another way for monomial realization of the crystal, which you conjecture that. For this conjecture, you say that we need some set of monomials, and then we just will obtain them from this Kirillov-Reshetikhin for infinite fundamentals, for infinite power.
Okay, so you mean, so in this conjecture, we consider monomial realization one by one, like MSK iota.
Yeah,
So your idea is considering considering the monomial realization for infinite product of highest weight vector.
Yeah.
Yeah. So but it's interesting idea. Yeah, but so I can't imagine what is the monomial realization of infinite product of fast monomials for now. Yeah, so it is interesting, but for now I have no idea it works or not.
Yeah, but at least all algorithms which we know, they will work for also for infinite the dominant. So if you have dominant monomial of infinite power, then doesn't matter. So it will be infinite. Answer will be infinite, but as expected for affine cases. But we can compute it, so we can. Okay, so maybe later we can just make some experiments to look if it sense question.
So have you tried it before?
No, just because I know that for fundamentals, so just in your lecture, you just give the discrete examples, then it's exactly monomials in for character fundamentals. So if you consider Kerr models for fundamentals, then it's exactly a new example. First and second example, it is just, but maybe it's we can start from A for simulated cases. So this is no in type A.
Type A, okay. This one?
Yeah. So this is first fundamental.
Yes.
And this is second fundamental.
Yeah.
So why did you stop? Why did you stop computing after this finite sequence? It should go on the sequence, right? Or
No. Anti-dominant.
But it's a monomial realization for fundamental weight, or what?
No. It's this Kirillov-Reshetikhin. It's not because in fundamental you will get one. So it will be not the anti-dominant monomial. So this is monomial in character for Kirillov-Reshetikhin for fundamental weights.
So it's a finite set?
Yes, so it's free monomial. It would be just sum. Yes, so if you just take sum, then it would be Q character of.
Yeah. Your story is about computation with Q character. Yeah.
Maybe you can write.
Sorry.
Of course, we can
make it precise.
Discuss later. Yeah.
We have other questions. I'm sorry, but we thank the speaker again.
Thank you so much.